Yeah, it's you can keep it on the floor, Gary, because you're next, I think.
Okay, let me go through and clean up my desktop so I don't get myself into too much trouble here.
Yeah.
Uh, the all right. I have a ridiculous
I managed to
uh,
get.
screen size, so I'm setting up the screen sharing now. Presume I'm authorized. I appear to be.
You should be.
And we're going to do advanced. Uh,
Yeah, things happening,
and
and yes, I see your
yeah,
screen.
we're almost there. Got a few more stray ones around. Uh, and we're now go and we put this up here and see whether or not. Uh, First off, is that become visible?
That looks good.
Okay, and let's see. Let's try this out. Are we still there, or have I blown things out of proportion?
Yeah, no, it came back. It took a while to think. It's still on screen. I think the previous one was slightly better format, at least
Previous
for my
one's better.
screen. Well, yeah, for my screen, I think that's a screen thing rather than.
Yeah,
Anyway, this works.
I have a 54-inch diagonal curved screen, a set of them stacked, so it
Uh,
behaves. And
no,
uh,
that works. This works
this one
fine.
works.
Yeah.
Okay, all right. My apologies for not having this untangled in advance. So we are good to go. All right, my talk today is going to be on sustainable lunar settlement design, more specifically the off-world anthropologic space infrastructure settlement, or OASIS. Um, I'm Gary Barnhard. I'm the Vice President of the Moon Village Association and the MVA Architecture Working Group Chair. I have multiple other capacities, but this is the capacity in which I'm speaking in this context. And my colleague, Abdulaziz Alareedh, may be able to join us. He's having to commute at the moment. What we're going to be talking about is a little bit about how this instance of a OASIS project has come to be, the science portfolio, the systems engineering portfolio, a better understanding of the outcomes and some element considerations examples, and what we perceive as the forward work in terms of the evolution of the broader notion of the OASIS project. From the standpoint of OASIS project as it stands, we have a situation where we started off as a activity under the Kepler Space University organizing team, which entailed, which has been an activity that's been going on since the beginning of 2023. The original participants included myself as the program manager and lead systems engineer, Abdulaziz as the OASIS chief scientist, Aisha Oren served as the OASIS lead architect for the 3 terms. And we had several other participants as what we euphemistically referred to as the Earth-based review team. Anahita Nazimi as the human factors specialist, Blanca Daraco as a design and human factors consultant, and Frank White as the Earth government representative. What this evolves to, though, is that the OASIS project, as I noted, began as a Kepler Space University initiative to develop a prototype simulation analog for sustainable lunar settlement. What it's evolved into is an effort to define a cooperative, collaborative, and competitive space preliminary conceptual engineering modeling endeavor, starting off as paper studies and leading in to efforts to, on a integrated basis, create a collaborative effort. The principal objective is to explore how outcome-based programs are driven by known science, systems engineering, and architectural design, such that they can maximize the probability of mission success. Should be noted that OASIS 2045 is the Moon Village Association Architectural Concepts and Considerations Working Group activity that was a case study of potential human lunar settlement to be established by the year 2045 and represents an ongoing body of work. And there are multiple other instantiations of the OASIS name in habitation studies. Part of what we're looking for here is this notion of finding nexus. Nexus in this case is the intersection between the science of what we know, space systems engineering reduced to practice, and enlightened architectural design. The OASIS mission development effort could be viewed as a set of conceptual threads intended to draw out the confluence of interests needed to bias work towards better outcomes. We are not trying in any way, shape, or form to be prescriptive with respect to what we're doing. We're trying to help figure out what it takes to make things work. The process goal is to reverse engineer the desired outcomes by orchestrating a combination of technology development push and mission requirements pull. Why space? If we're going to dive into this, we better have some foundation in those regards. In these challenging times, the importance of our investment in providing for the future, including space exploration, development, and settlement, should not be underestimated. It serves as a foundation for hope. The vast resources of space, energy, material, and the potential for habitable area are potent enough variables to transform the fate of our species. It affirms that we're a resilient species in society that will not be deterred from lending our efforts to forging a brighter tomorrow. Effectively, we dare to dream and see that dream made a reality. To which the OASIS scenario is that the signatories of the Artemis Accords, united in their collective determination, have set their sights on the successful development of sustainable off-world human settlements as a shared goal that must be realized. Furthermore, this goal is best served by a combination of cooperation, collaboration, and competition. This effort to architect, engineer, and implement anthropologically sound space infrastructure for settlement purposes is intended to support a realized arcology. That is I found an interesting way of putting it if you, in terms of analogies to various faith traditions, in terms of what is or is not realized that someone might wish to explore. The project objectives are to manage the cost, schedule, and technical risk of the same in a manner that allows it to be actualized within a decade. Actualization can be by direct implementation or infusion in other nation state and commercial infrastructure. When we're talking about driving requirements, this is a bit of an eye chart, but it's intended to be an introduction to the other phases of this discussion. We have there are things that we know with respect to the science, things that we know with respect to architectural design, things that we know with respect to systems engineering. An awful lot of the science is really based on the ground truth of what we found there and what we understand about the environment. An awful lot of the architectural stuff is the dynamic tension between the notion of form following function, except for when it doesn't. And this notion of arcology, which really is the relationship between life, the natural environment, and the built environment. We in systems engineering, we have this, the collision with reality that necessarily has to occur in terms of how we understand what we should be building and how it has to work together. Not just as we intend it to, but what happens when things go wrong. Aziz, were you able to join us yet? I haven't been able to see. I guess the answer is my colleague has not been able to, so I'll proceed on in those regards. In terms of the science portfolio, breaks down between space physics and moon physics. Outer space, we've got to deal with the different aspects of radiation. We've got to deal with the lack of a magnetosphere with respect to the moon, as well as interaction with the Earth's magnetosphere in those regards. And of course, gravity is a consideration. In terms of the moon physics, you've got the environment of the lunar landscape. Several things that are particularly interesting from a habitation standpoint to look at is this notion of lava tubes, skylights, sky vents, even when they're spelled correctly. Sorry about that. Pit craters. And it turns out there's a combination or relationship between these that play out with respect to the broader notion of what's really the structural characteristics of these different aspects of the environment. You dive into the space physics. You have the variety of radiation concerns that you have to end up coping with. Different interactions that are possible. We have a fairly good idea of what one can anticipate with respect to dosage ranges, what works and doesn't work, for life as we know it, and how to structure the problems, at least how to structure the problem and work towards solutions. In terms of the physical habitat conditions, obviously this notion of ground truth is critical. What constitutes the acceptable radiation levels, how we cope with the regolith problems, the illumination of the habitat, the temperature and humidity that have to be able to be addressed in a passive fail-safe state, and the atmospheric pressure considerations. What we have to end up as we dive further into this, we've got to find the locations on the moon that are most suitable. We have to deal with how it is that we're going to mitigate the radiation hazards in using passive fail-safe states as a standard. Cope with the different approaches to coping with the regolith, natural and artificial illuminations, how we're going to maintain the temperature, humidity, and the atmospherics of the same. The idea with respect to this is it's not just a recursive problem. It's not just an iterative problem. It's a recursive problem as we layer in these additional levels of detail. And what we wanted to be able to show from the science side is that what do we have to do when with respect to these issues and the path forward. I've got to get that out of the way. And in particular, things like the ground truth needs to be established before construction begins. We need to address at least all of the known health risks and how we can deal with them. We should any design up front's got to deal with the radiation, illumination, and temperature and atmospherics. There are seismic activity on the moon that has to be contended with and addressed in all of the structural systems enveloping all anticipatable events. There's electrochemistry considerations. We saw a lot of that in earlier presentations, and how it is we're going to make in situ resource utilization work. This is gives you an introduction to the sort of locations that we're talking about. These are several examples of what's a lunar sky vent. What's down at the base of that sky vent has been an issue of much speculation and significant research, as you see in the inset image there. There could be quite expansive areas in terms of the lava tube underneath that, or it could go straight down. And everything's collapsed around it. It remains to be discovered. What we're looking for, though, is that for the purposes of the OASIS project, is a sky vent on the order of somewhere between 70 to 100 meters in diameter, and approximately 100 meters in depth is assumed. And there seems to be a range of them, in that size range. From a modeling strategy, the main grouping, is the implementation and the design construction of the OASIS into 3 phases. The phase segmentation is based on the science requirements as well as the engineering and architectural ones. The science constraints both adhere to the physical conditions of the lunar surface and the whole range of characteristics that we had outlined there. And the results will be collected from phase 0 and 1 science investigation. How are we doing time-wise, Nicholas?
Yeah, you're fine. The presentation after yours is being cancelled, so you can draw over.
Okay, all right.
Or rather, it was me being after you, really, but I had my presentation at the beginning because that speaker never turned up.
Okay, well, just at least give me a 10-minute warning, okay?
Yep.
Okay, thank you. In terms of where we looked at it, is a bit of a sequencing effort from a science perspective. Where leading it through, what we laid out is the areas of focus, the concept and design R&D, testing verification, and modeling opportunities. And we had a sequencing for phase 0, phase 1, and phase 2. Now, loosely put, phase 0 is essentially the analog work, both Earth space and the LEO and other testing opportunities. As they become available, phase 1 is going through and addressing in situ testing, to finish driving up the TRLs and ensure that we've got got the designs right. And then phase 2 is the implementation at scale. I foreshadowed myself here. Okay, so again, the phase 0 is Earth, both Earth-based, spaceborne, and the beginnings of taking advantage of the best available lunar surface data that we're able to gain from the various campaigns that are planned. Again, this work is not in any way, shape, or form intended to be preemptive or worked in isolation. It's intended to try and leverage things that are being done across the broader community of lunar activities. Phase 1 would be really cislunar and low lunar orbit, establishing core communications and navigation infrastructure, and the lunar surface testing in terms of regolith and radiation conditions, building an assembly of different robotic structures, building the first full-scale habitat unit, and the crew and operational resident operation phase of phase 1, and starting preparation of the phase 2 site, and your phase 2 being the implementation at scale. What we're going to proceed with now is into the systems engineering section, diving in a bit deeper on the systems engineering requirements. The launch mass versus functional mass is a very important trade space to consider. One of the things that is worthwhile to bear in mind with respect to this is historically, essentially everything we've flown in space, with the exception of a certain Tesla vehicle, has been designed, has been hyper optimized with respect to size, weight, power, volume, what have you. Given that we have a situation where there's at least one vendor that is proffering the notion that they can drive the landed cost of a kilogram on the moon down by between 4 to 5 orders of magnitude. To put that number in perspective, if you achieve the 5 orders of magnitude, it would be cheaper to land a kilogram of mass on the moon than it would to ship it from the continental United States to Alaska. One might argue that that's being a bit optimistic to the point of extreme hubris, but there's something else going on here. When you look at it from the terms that at some point in time, and I postulate it's probably a 3 order of magnitude reduction, you can go and change your design paradigm. You can go find things that do what you want it to do on a terrestrial basis, leverage that technology, and then optimize that for space. Because suddenly swap or the size, weight, and power is not the driving requirements. Your functionality that you're able to deliver is the driving requirement. So this launch mass versus functional mass is a very important consideration. You have to cope with the volume, the payload volumetrics, which are not only mass and volume, but CG and the peculiar aspects of any particular launch vehicle, the logistics and handling, the notion that you need to provide for not only EVR or robotic compatibility, but EVA and IVA compatibility for a lot of the ORUs where you may wish to be able to fix things down at a component level. What we heard in one of the earlier presentations, this notion of how it is that you really deal with issues of structural dynamics and structural integrity becomes a critical thing. Designing for maintainability, becomes a critical factor, and it's twins of reliability and availability and all the other illities, if you will, including interoperability, and then our articulation of how we take these requirements and build them out as distributed systems and elements. And what you see in terms of how this, we had to make a number of assumptions with respect to the OASIS project. We're predominantly working at the level of the Starship infographic data for mass and volumetrics. We're assuming time trips between the Earth and Earth orbit and the moon, approximately 3 days. Logistics runs would have to initially be more on the order of once a month, heading to once a week, based on the sort of flight volumes that SpaceX is designing for. There would be some notion of assembly one-way runs that could be defined, passenger runs that could be defined, payload offloaded at a landing pad. There are, NASA's let out contract. I don't think it's technically an extension, but it's an additional design point in terms of cargo, only versions of the transport. We have to address the issue of local transport to the OASIS habitat. There's this notions that if you look at things from a logistics standpoint, middle latitudes with a direct view of Earth are actually far more tractable for a whole range of reasons. Perhaps it's more like Antarctica in the sense that McMurdo Bay, is a staging area, and sorties are deployed from that. There may be some key analogies there. We need to provide varied means of access to any sort of OASIS, shuttle bay or hangar bay-like environments, and including, if we're going to minimize regolith, impingement, vertical access to the shuttle bay. This notion of redefining our notion of orbital replaceable units to provide for the various compatibility concerns, structures that need to be designed to be self-damping, self-supporting, and non-unzipping. That it turns out, this is a thing both with solid structures as well as inflatable structures, and we may end up with hybrid structures. All systems and elements shall be designed to be maintainable indefinitely. This is one of the things that we need to factor in terms of our factors of safety and in considerations in design elements. We need to be building something closer to a DC-3 where you don't have to even worry about airframe hours than something that's designed to work in testing and once in use. All systems, all critical systems and elements, I think should be two-fault tolerant at a minimum, shall use common spares wherever possible, and shall be functionally interoperable in some number of ways to provide further redundancy. And we're as I said, this is not just an iterative but a recursive thing where the level of detail of these driving requirements needs to be taken further and further. We do have, as I alluded to on the earlier chart, we have made a number of assumptions here. I'm not going to repeat them so much as emphasize the fact that things like the structural dynamics and integrity, this notion of having self-supporting, self-sustaining structures throughout OASIS, effectively what that can do is leverage our understanding of in-space structures to be able to ensure that we have elements and distributed systems that are not reliant on any assumptions we're making about the moon. That is, I would believe, is the most conservative approach that we can take on this, and something that would be instrumental. A key thing from a systems engineering perspective is figuring out what the top level requirements are that you're going to work to. An example of this is that in the space station program, where I own the system level requirements for advanced automation and robotics, I successfully made the case that the space station remote manipulator system defining load should be the ability to accommodate a fully loaded space shuttle, both payload bay and crew. And that ended up driving the design in some respects of every element and distributed system on the station. But it turns out it was the right thing to do, because that means that system performance enveloped anything that would be asked of it on the International Space Station. We need to drive out what the key requirements have to be on each of the elements and distributed systems for sustainable lunar habitats in a likewise sense or manner. I mentioned the notional Starship design specifications. There's a lot of play in this in terms of they're looking at lengthening it, they're looking at how this can be optimized, but this was our starting point, and gave us a basis for going forward. When we look at it in terms of defined elements, we've defined what amounts to being 5 major categories. What amounts to being habitable module elements, which consist of a combination of hybrid fixed, unfurlable, and inflatable modules. And in all likelihood, a significant number of them may be some combination or hybrid, if you will. We have to provide for private space, workspace, including common rack systems, shared space, and safe haven provisions, both in terms of consumable resources, ingress and egress, and two-fault tolerance systems with passive fail-safe designs, truss elements, both deployable and erectable stabilization platforms. This is, again, harkens back to some of the earlier presentations that we've had today, where you have to figure out how it is that you can make the necessary structures to be able to react to loads appropriately, accommodate the necessary utilities, provide for not just enclosed volumes that are pre-configured, if you will, but also that are erectable, including things like a hangar shuttle bay, which is not is not something you're going to effectively inflate. Okay, you're going to have to build it from pieces and have them connect together. And also we have to figure out this notion of temporary payload handling and storage. Going through and building truss elements that can perform multiple functions in those regards is going to be part of both the systems engineering and architectural art, if you will, of element design here. This notion of atrium elements, they have to provide for mobility paths. They're a form of, architecturally speaking, of negative space. You could think of it as pressurized open areas. There's also the aspects of space frames as hemispherical canopies, and the notion of space frames as toroidal volumes with internal load reacting pylons, which comes up in our phase 2 design. Then we have this notion of connection node elements. We starting off with the common hatch interface standard accommodations from the world of the International Space Station. The notion of common utility interface standard accommodations, again looking at ISS, Gateway, and the various emerging consortia activities, which we'll get to shortly, and the notion of some form of common airlock mechanism accommodations. And we've also defined this notion of the XISP Inc. air and water lock mechanism accommodations. There's some very interesting opportunities there that take advantage of the science of what we can understand with respect to electrostatics and the behavior of things that have emerged from our discussions here. In the fifth area is mechanisms and specialized electromechanical equipment. The air and water locks, which I've identified, the notion of robotic systems in terms of large-scale remote manipulators, dexterous manipulators, tools, and equipment handling. It has to provide for both assembly, operations, and maintenance. And there are various tools in terms of equipment, material handling, and transport that have to be provided for. We need to arrive at a means for dealing with observations and inspection systems. This notion of the core shuttle bay lift and auxiliary elevators and lifts, crane components, a deployable landing pad, grid mats, and deployable self-driving auger anchors, for example. And we've gone through and laid out what we think in terms of the distributed systems, key pieces that need to be provided for, across each of the elements at some level. This is our starting point in terms of the conceptual sketches. Basically, we've got to deal with the sky vent volumetrics, light and radiations. This is shown as a cross section. And the idea is that we know that, if you get below 20 meters, radiation is pretty much a non-issue. with respect to being below the surface of the moon. The number may be a lot smaller than that. We wanted margin, okay, because there's not only you have a situation where with respect to light, of course reflects, okay, and we can take advantage of that for both natural illumination and artificial illumination. We can, however, radiation fragments, and we have to provide provide for that, and so that the essentially the we're presuming that the first 20 meters are going to be areas where there's significant mechanical infrastructure and provisions, in addition to the provisions for passive radiation protection. We've also pointed out that there's a difference between what constitutes the the central core, if you will, with respect to the protected habitats, elevators, equipment, elements, basically the elements that will be bringing in some degree of open volume to either side of that, and then the treatments with respect to the sides or walls of the sky bed. We don't know what they are in a very real sense. They may be something that you could literally just put a coat of paint on or center to create a working surface to deal with. Worst case is you have to build some form of lunar concrete retaining wall, which we also looked at, essentially as a pre-stressed concrete, implementation using cables and rebar under tension, with from a lintel, down to the foundation. And we also intend this to be something that could expand up to 500, accommodate up to 500 people within a single area. So we're building in this notion of expansion areas, and there's always the opportunity that if there is a substantial lava tube down at the base of that sky vent, that we can build into that area. But in order to establish the habitable capability and an environment where you can be doing all of the necessary ground truth experiments with respect to processes and different approaches to dealing with things, you want an environment that is sustainable and is under your control and allows you to access the other aspects of the environment. And what you see here up at the top is, you'll see in more detail, is this notion of some form of erectable space truss at the top that allows for vertical access into a landing bay, and some reflective surface to allow natural illumination to come in, as well as artificial illumination, and some form of structural lentil space frame truss, which spans not only the sky vent but a significant area surrounding the sky vent, so that the bearing strength of the lunar surface material can be allowed to be an open-ended area of further exploration. This is an overview trying to show the Skyvent truss platform notional construction. We started off with essentially a 10 meter by 10 meter truss size, which means that each one of those trusses, you could actually take something that you've unloaded from a starship and fit it in to that truss to guide it through, with the appropriate mechanical systems through to the what amounts to being the elevator system, and before the elevator system, the necessary craning tools to handle things in a safe and reasonable manner. And we basically are a lot of what we were involved with is understanding what are the dimensions in terms of how you would have to divide the space versus what the surrounding area needs to be. We looked, at the volumetrics from a number of perspectives, both from the basics of of a lava tube versus what constitutes the different interplay between the utility volume, the habitation volume, the atrium volume, and what the phase 2 volume might be. And we also compare that to a whole range of terrestrial analogs, going down into, what amount of space does a human need versus, to survive versus what to thrive. And we went and actually looked at building codes and, the up through, other examples of what constitute places people would like to live in and do live in. As noted, OASIS is intended to be a realized arcology. What that turns out to be is this, this notion is the shared understanding of the relationship between life, the natural environment, and the built environment. Concept was championed by Paulo Soleri, a visionary, Italian-American architect. What is life in OASIS? Okay, essentially what we have to go through and do is figure out from, what's the tree of life going to be? Once we leave Earth in those regards, there's been many in media, various science fiction characterizations of humans as ugly giant bags of mostly water or liquidious flesh bags. Bottom line is we don't travel alone. Humans require both their internal and external biomes to survive and thrive. When what we've gone off and done in terms of the OASIS project, looking at the built environment, we've taken a dive into each of these array of questions at some level, and the point is to take it to the point where we can start making connections between disciplines, start making connections between work that's been done by others. The curious thing about building spaceships, when it comes to building spaceships or cathedrals for that matter, they're not built by individuals, they're built by teams. Okay, and that is critical to this, and we want to find the way to open up this discussion for the broadest possible meaningful interaction. What's the natural environment in OASIS? Again, you see the reoccurring themes and the information that we've dived into, and I'm going to provide some examples of this in the presentation. This is an interdisciplinary design process, where every object, in our arcology and spider diagram here, is really part of a taxonomy that was considered and discussed from the vantage point of science, systems engineering, and architectural design. And, as I said, you can dive into, each aspect of it. It's not definitive. It needs far more, far more in the way of, references and, the building on the analytical foundation. But it represents a fresh look of how to structure and organize, the knowledge associated with the different, domains involved here. Again, the phasing is 0 analog test, 1 in situ testing, 2 at scale deployment. We, took a strong dive into this notion of what amounts to being self-supporting, self-sustaining structures and structural integrity, if you will. And, started off, with the, plutonic solids and tried to find our way that would give us a path towards things that are both that have structures that exhibit the characteristics that are the requirements are driving us, and achieve other other aspects associated with the logistics of packaging them, deploying them, and what have you. This evolves into something that's actually rather curious when you dive into it. There's this notion of a kissing number, which is what shape an object can be that can allow it to be in its closest position to its nearest neighbor. And in a 2D planar space, a hexagon works out very, very nicely in those regards. And actually, there's a relationship between triangles and hexagons that's illustrated here. And then when you take that into 3 dimensions, it turns out that there, even if you go to a sphere, which is an infinitely sided structure, there are this kissing number turns out to be a thing. We have a relationship that has to exist between the stowed habitat module payload, the deployed habitat module payload. This uses the expansion factors of the life module being worked by Sierra Space. And then the notion of the fact that we have to go through and extend this to go through and understand how they could be aggregated. And we make a distinction between what constitutes the various rings of modular elements and the central element, which has turns out to be a combination of both positive and negative space. Excuse me. We had to work the connectivity issues very early on. Driven by both the stowed volume and the deployed volume that we were working for. It turns out this drives out the requirement for a connector node. This is strange but true. We had the same issue in space station, and we ended up with nodes. So this ends up being part of how we derive the requirement for it, and part of what we've tried to do, which was test the requirements as we went to provide the basis for them. And you can see what we're faced with in terms of the stowed volume is accommodating both the Starship wall or the other landing systems, the dynamic envelope and the stowed payload envelope. We have and when we go through and we look at what we've arrived at in terms of a structural alignment, there is this ends up having a two-way relationship with science requirements, the systems engineering requirements, and the architectural design requirements. We have some scale, this adds another level of detail to the scaling and phases. We're looking at a population of 6 to 12 for the analog activities. What we designate as phase 0, and it would, we think, eventually result in the equivalent of a 5 to 10 person lunar population, still within phase 0. Phase 1 is more akin. Its analog would be the logistics space at McMurdo. You're looking at a 10 to 50 person lunar population that we postulated for phase 1, and a sustainable settlement in phase 2 from 50 to scalable to 500. There's this notion that one of the earlier presentations pointed out with respect to tensegrity. There's a relationship between tensegrity and tessellation and kissing numbers. It turns out that One of the things that we have to end up coping with, particularly in dealing with things like micrometeorite, impingement, on our site, and the fact that we've got to have things that, are maintainable and meet requirements for accommodating mechanical systems that allow them to be open and closed, and in some cases, transparent. In other cases, requiring various forms of mechanical attachment in openings or apertures to move through. So this is an example of our exploration of that for a canopy that could implement effectively a stuffed Whipple shield micrometeorite protection capability. Under tessellation, we have to look at it in terms of the hybrid fixed, unfurlable, and inflatable structures we've been talking about. We want to react the mechanical loads to fixed and unfurlable frames. The notion of using a pressure bladder that fits in and is contained by unfurlable frames, I think, is a novel approach that we're offered up, and it's a combination of geodesic and Gossamer structures. From a kissing number standpoint, we've got to address the optimal packing designs for 2D and 3D. And from a tensegrity standpoint, we're looking at a combination of erectable structures, self-supporting structures, and self-sustaining structures. And where erectable structures come in is that we need things that can support themselves while they're being built. Okay, they can't be a pile of pieces that don't come together until the last piece is put in. Okay, they have to, support themselves during the process of erection. When we look at tessellation in 3D space frames, this is another somewhat novel thing that we've looked into, is how you could go through and use tetrahedrons with a minimum set. We've defined what amounts to being a standard set of struts that would be EVA and EVR compatible. These have been analogous things have been tested in both ground labs and space labs associated out of the space shuttle, and also on space station. We've also been used in a variety of different spacecraft designs where you have the standard struts and standard vertex nodes. The idea of telescoping struts, however, that can be extended or retracted, now enable you to take tetrahedron structures and have them go flat or curve on any to create any form of contoured surface that you'd like.
Gary,
Yes.
you have been talking slightly more than 50 minutes now, just so you know.
Okay, all right. Cool.
You're fine to continue a bit further.
Okay, all right. So what we've done for phase one is look at what an instantiation of these elements, how they might fit together, and how these requirements can be accommodated. We went through and presumed that we'd be using a nearby crater to a sky vent that would enable both the canopy that we've shown and multiple instantiations of the elements that we've defined to be arrayed and tested to see what we're doing right and what we have to fix. And this is another view of that shows the canopy in cross section, and the idea that it is something that actually would be supported above the surface of the base of the crater, so that at a level where there would be interaction possible and you could go underneath it with both vehicles and people. And we need to be able to show that there are expansion capabilities. This also introduced this notion that the interconnection modules in a variety of instances would be useful to be relocatable, and we have to understand how we're erecting the central, core space as both a combination of positive and negative space to create the hangar environment. We have a series of key interfaces from an architectural standpoint. The sky to the atrium, the atrium to reflectors, atrium to atrium, and regolith to mechanical systems of how you secure things. Conceptually, that's laid out in the schematic to the left there. That where we have to go through and address each of these, and there's a relationship between tensegrity structures, gossamer, and geodesic structures here. This evolves to this is a conceptual volumetric, cross section. The idea being is that we have a need for providing for the spaces identified in the left-hand legend, and the proportionality is one of the things we had to come to understand as part of the study efforts. This is intended to say we need these pieces, and we have to understand volumetrically how big these pieces should be in relationship to one another for any instantiation of a OASIS-like habitat. We talked about the notion of the cargo versions of both the SpaceX and Blue Origin team, which are shown in these recent artwork. This is what amounts to being the terrestrial analog example. We need closer, this notion of the, what where I think we need to head to is closer to is evolving those cargo designs to be more like a C5A. I guess it's up to C or D or something now. Dating myself. And we also went through, in another example, we looked into the landing pad concept of going through and being able to take, hexagonal stainless steel mats and use them as something that could then be heated up in a variety of ways and used to essentially, create a ceramic out of the lunar surface material that could deal with the necessary blast effects that would be present, or thrust and pigeon from the use of the landing pad. Let's go to the next one. There are, and we worked through the comparison to the logistics, and it's important to point out that in terms of our experience with respect to the Antarctic, logistics is like 70% of the problem. Okay, as some of the researchers have pointed out, we've looked into some of the notions of the approaches to funding for such endeavors from a commercial standpoint. You can have approaches where you're taking terrestrial markets to generate surplus cash for the IR&D, sort of a go as you pay, cash flow driven model. There's this notion of pay as you go, which is a cost of debt service driven. There's the notion of how you go is what matters, a process driven approach, which is really looking at the knowledge of the problem space as a capacity building exercise. Where you go is what matters, an outcome-driven notion based on the knowledge of the potential solution space. As a consortia for mission development and execution, basically leveraging in-kind resources and cooperation and collaboration. There's equity financing approaches and blended financing approach. And then there's this notion of being able to use light duck-based project financing. If we can go through and define a project where we're doing X, which is understood, and it just so happens to be on the moon, we may be able to achieve some bounding of cost, schedule, and technical risk. There's the mega project, the public-private partnership approach. And based on expanding the economic pie to leverage space resources to catalyze the progress of the United Nations Sustainable Development Goals and any number of other things. We've done these things before. This could be another instance that makes that happen. From a forward work perspective, we've got a series of papers coming out for IAC 2024 Milan, as well as popular press publications. The importance of EVA, EVR, and IVA compatibility at some level cannot be understated and must be addressed for everything that's launched. The accommodation requirements and interface standards are needed. There's consortium coordination possibilities in terms of the Lunar Surface Innovation Consortium, LSIC, the Consortium for Space Mobility and ISAM Capabilities, COSMIC, the Lunar Operating Guidelines for Infrastructure Consortium, LOGIC, and there's the essentially the OASIS specific consortium, which thus far consists of the Kepler Space University, the International Astronautical Federation, working with the Space Habitats Committee and the Space Systems Engineering Committee, the Moon Village Association efforts, and the Space Development Foundation and Extraordinary Innovative Space Partnerships work, and any other
that was the egg timer. So if you wrap up now, we can have some.
This is
have
we're
some
on my
time.
actually my last slide.
Good.
Right. So there's importance in working through the intellectual property issues before it becomes a problem. In the various elements of intellectual property need to be addressed. We have things like the process definitions, the characterization of the problem space, and the characterization of the solution space that actually can support cooperation, collaboration, and competition. The concept of the conceptual round robin is an integral part of the processes involved. In a realized arcology, I believe is critically important. How we foster the expedition mentality to provide team cohesion when you have a mixture of cooperation, collaboration, and competition is critical. We need to not lose sight of the fact that sometimes the truth is stranger than fiction with respect to how this stuff works out. And let's not wait for the future. Let's work together to build it. Thank you.
Thank you. And we do have some questions. So anybody who has asked question in chat who wants to ask it directly, we'll take that first. Okay, doesn't seem so. So let's go back. James Sloan had a comment. Only a few days ago, here was confirmation of sizable caverns beyond the sky vent.
The answer is that work. Actually, that's been. It's interesting that's suddenly resurfaced as news. Okay, there's been a variety of data, which I just showed a little conceptual cross section of that said it really looks like there's something down there. Okay, and the off-angle camera views that they've been able to get of various sky vents, including one we're looking at, seem to be very much indication of the same, and that was what was reported out in the news, I believe, and it's neat stuff, and we need to create an environment where we can learn to work with that without making any assumptions about what's there, in order to be able to provide our working the ability to work there.
Yeah, and then we have well, there was another question. That's also a comment. I'm not sure I can place that. That is equal to 3 times the Earth's atmosphere radiation. Oh, it's about a 20-meter rock, I think.
Oh, yeah. The idea is that we know that it's at least 3 meters, okay, and we know that there's going to be some structure that we have to cope with. We don't know how much, okay, and by going through and assuming, we also wanted the hangar bay to have sufficient height to accommodate payloads in incoming and outgoing local transport. So by assuming the 20 meters was an interesting assumption, they could envelope all of those requirements.
Yeah, I'm a caver. We used to say that 20 meter of limestone has very good sun protection factor.
Mm-hmm.
Anyway, and Doug Plata has commented that skylights are not near the polar volatiles. So yes,
That's correct.
likely, but lava tubes later.
It's closer to the middle latitudes.
Yes.
Hence the fact that when you factor in the logistics considerations, it may be that the staging area in research facility is perhaps best located closer to the middle latitudes, okay, to take advantage of those structures, and you run sorties from there. The idea is that given that logistics is such a driver based on our terrestrial analog experience with Antarctica, and it's not going to be the likelihood that it'll be less of a driver in lunar activities, is not high. We think that there's a case to be made that being closer to the middle latitudes and the sky beds is a good idea.
Yeah, maybe. Yeah, okay. I think that answers that question. Frida has said that space habitation and Earth's archaeology space habitations and Earth's archaeology need to convert wastes to resources. Space ecology's contribution to Earth's life support systems.
Oh, absolutely. And one of the great things about this is even if you never built it, if you figured out how to make it work, it's all directly applicable to Earth.
Yeah.
Okay. It's the idea is that if you go through and you maintain things like the structural self-supporting, self-sustaining structures and things like that as an integral part of this, it ends up for free space habitats, it also ends up making sense. So there's a whole range of things here where there's synergy opportunities, and we need to just as are the great talks on worms and in chemistry that we've seen today. These are all an integral part of the deep dives into the details of making this stuff work.
Yeah. A good point about any work that is being done on Earth can be used. That is being done now can be used in many settings. That's my philosophy as well.
Well, thank you all very much. Are there any questions that we've missed?
Let's see. Yeah, that's. I think those were that. Yeah, no, I think those are.
Cool. And Nicholas, is it your intention to make these presentations all available?
They will be. They are being recorded. My intention is to slice them into separate presentations as the entire day is being recorded, and that's a bit.
Are you going to make the charts available?
Now, not except as the presentations. I mean, they are. I could. I think.
Yeah,
I haven't thought of it like that
I would be supportive of the same. Okay, and if you need any web resources associated with doing so, I know the guy that owns xisp.net, which is the only publicly routed node on the Verizon Fios network, and I've got 3 6-way blade servers at my beck and call. So
that sounds useful.
The Space Development Foundation does that for the annual Space Solar Power Symposia.
Okay, that's good.
All right. Well, thank you all very much. I appreciate the opportunity, and you'll be hearing more about OASIS, and we're encouraging other folks to get involved. both, and the Moon Village Association Architecture Working Group is trying to help extend this further into multiple simulation environments.
Actually, I had a question there, maybe a bit complex one. What is the business idea for this work? In a wide sense, obviously. Who are you selling this base to?
Well, what
the concept that you have been describing,
right.
who are you expecting to use it?
Well, where we're coming from on this is that if you wish to go through and understand what it takes to deal with ISRU, what resources can be obtained from the moon and effectively utilized both there in lunar orbit and GEO, MEO, LEO, or what have you, or throughout the cislunar space. You need a laboratory environment where you don't have to simulate everything. You can actually test it, and in the environments. There's a whole series of different things which we would like to understand, which I sure as hell would prefer them not to be done on Earth. Okay. So from an isolation lab standpoint, there's something to that. There's this notion of what what are the component technologies when you go through and you do something on an outcome driven basis where you're taking the work vector continuum from ground technology development, space technology development, to demonstration, to deployment in actual systems. How can you go through and if you do this not as a one-off exercise, but essentially as a learned process of learning how we can reduce systems engineering to practice. There's a whole series of what amounts to being pieces of stranded intellectual property on the wrong side of the technology development valley of death, which can be curated.
So essentially, what you're developing the process of making a moon base for whatever application on the moon or elsewhere, rather than actually designing a moon base.
Right. We are not a priori trying to be prescriptive here. We're trying to go through and understand the process so that when you go through and apply it, it results in a better outcome. Not just for the moon base, but for the understanding that can be translated to terrestrial or any other form of arcology that you're trying to make work.
Yep. Okay. That answered the question. Thank you. That was quite interesting approach. I like it.
Thank you.
So let's proceed to the next speaker, who is an author and presenter, presenter now, obviously, Alastair Storm Brown, who is the co-author of Cosmic Careers, and he's a master in space studies from the University of North Dakota, and he has done presentations and written various articles, including the book Cosmic Careers. Please fill out what I missed in the presentation of your Alastair Brown. Let me see, do we still have him here? Did he disappear? That's scary.
Nicholas, it's possible he just went for a break since he's not scheduled for another 15 minutes.
No, I've been chatting with him, so he was ready to get in earlier. And yes, thank you for pointing it out. Yes, he was scheduled for 15 minutes from now, but he was going to get on earlier. So, okay. He probably left. I said 10 minutes, 8 minutes ago, so he maybe went for a short technical break anyway. Yeah. Any more questions for Gary? Or any more comments from you, Gary?
Well, one of the things I suspect, that's important, I think is terribly important to understand is this, what's going to happen with respect to the landed launch costs. Okay, if it really does, if what is achieved with respect to the different human lander systems does make it to the 3x reduction, I believe it will fundamentally alter the design paradigm for things that are lofted in space, at least from an infrastructure building standpoint. There'll always, be situations where you'll have things that are hyper optimized, but the idea that you can alter the design paradigm such that you can find something that actually does what you need it to do first and foremost, okay, and then optimize it for space would be absolute, I believe, absolutely transformative. So that's something to bear in mind. How we achieve systems that are self-supporting and self-sustaining, it can get arcane pretty fast. But I love the discussion venturing into Femin, and understanding the analytics. I realize the set of folks that are really interested, much less prepared to discuss structural dynamics, is a really rarefied community. And it turns out that's part of my academic background, in graduate and undergraduate school in structural dynamics and materials science. So I have a fascination for such things. And perhaps I've read an awful lot of Buckminster Fuller in my days. But there's something that's important there, and it makes a difference because if we do it right, we don't have to have all the questions solved in advance for what it is that we would like to build in terms of infrastructure and structural habitats on the moon, or sustainable habitats on the moon. We can take advantage of the fact that we are able to provide what's necessary for us and learn how to best utilize the environment, as opposed to having to figure everything out in advance, or worse, assume that something's going to be there and it turns out to be different than what we assumed, and it creates a severe problem. So those are this notion of, in a sense, top level or driving requirements is something that we can make a substantive contribution to anything that was done as a specific direct implementation of OASIS, or for that matter, any infusing what we learn into any program of record that goes forward, regardless of whether or not it's nation state driven, commercially driven, or some combination of the above, which quite frankly I think it has to be.
Yeah, I think I kind of agree with that. You can design human sustainability as a kind of independent project, and then you can tweak it to whatever environment you're in.
Right, and we're in this boat not just for us. There's something called life as we know it. Okay, those spider diagrams aren't an accident. There's a whole set of relationships that exists between just the small number of things that we called out there. Okay, that we happen to have, at least gone to, some trouble of diving into. And there are folks with extraordinary expertise, and in many of those, and many that haven't yet been added to the appropriate diagrams. So what we're trying to go off and do is provide some bait, provide some catnip, if you will, that will get people interested in exploring how we can make cooperation, collaboration, and competition work. And we actually have done something interesting with NASA in those regards. We're one of the few organizations that have been able to negotiate a Space Act umbrella agreement with NASA, where the idea is that you can have a mission where the government can make facilities available, hardware, software, civil servant labor, contractor labor, and put it in to either accelerate milestones on a mission or add milestones. And commercial entities can do the same thing, and it doesn't require a procurement exercise. If you want to have an exchange of funds, there's overlays that can be gone through and implemented in either direction as other transactional authority. But a priori, to figure out whether or not there's a basis for cooperation and collaboration doesn't require an arcane procurement exercise.
Yeah. And never mind that signal, because we still don't have Alastair here, so we can continue with some kind of discussion. And anybody else from the audience that want to pitch in on anything actually from the entire conference, feel free to do so. We need to pause some time.
Nicholas?
Yes?
This is Doug Plott. I got a question for Gary. Do you know what the Moon Village Association's understanding is of the transition from a government, international government base to private settlement?
The answer is that we in our activities with respect to the architectural working group, that is part of what motivating that understanding, such that what we've seen with respect to statecraft, this is venturing into a bit of the United Nations stuff, is that agreements that are based on a clearly identified confluence of interest tend to be widely supported and subscribed to. Activities in statecraft that are not based on a clearly articulated confluence of interest tend to flounder and fail miserably, which is what we saw with respect to the Moon Agreement in terms of the very limited number of folks, and to my knowledge, still no spacefaring nation has actually signed up to it. There's some ambiguity with how you classify Australia, I think. Okay, so what it amounts to is that how do you go through and inform the well-meaning folks that would like to write lofty words? There are things like the Artemis Accords, which are a starting point at trying to draw out where an identified confluence of interest, but there is much more that can be done to bias the activities towards success. And if we can construct a vocabulary that enables us to inform the discussion and how a confluence of interest is drawn out, that would be a win. Okay, engineers are good at answering questions of how to get something done. Okay, how to hold forth and motivate people to doing the same, maybe not as much. Okay, so as much as I might like to agree with with Shakespeare in those regards and kill all lawyers, there's a point to them. Okay, we need to find way, our understanding of what constitutes commercial, commercial space is different than a lot of our allies and would-be competitors or adversaries in those regards. We need to figure that out. Okay, and it has implications. Not just in very specific terms, but in the broad terms of how we deal with our relationship of extending our civilization, beyond the biosphere.
So Gary,
we got a lot to learn.
yeah. So it sounds like TBD for everything. What I would say is, I think that my opinion is, I think the Starship fleet, with considering SpaceX's engine production rate and their construction of their finishing up of the Starship factory, makes the concept of a Starship fleet as probable. I think it's likely going to become a reality, given the reality, which I think is the dominating reality for any future plans. I would see that the first tickets are probably going to be the most expensive, and then as flight rate increases, the per seat ticket price is going to decrease. But with the first tickets being the most expensive and the need for SpaceX to recover its investment, I do see a large international lunar development phase, lunar exploration phase and lunar base phase. But as the flight rate goes up and the size of the fleet increases, I think the per seat price could come down to what wealthy individuals could afford. And so I think there's going to be a natural transition from international base to private individuals, basically just paying the companies who have already been paid by governments to develop the habitation and life support and food, technologies, sanitation.
Tech.
Yeah, they just incrementally crank it, and they just keep adding on to base. But now these are private people attached on to.
So my question to you, Doug, is that there's something that's happening there. Is that you just change in the paradigm of how it is that we design things for space. Okay, once you can go through and start taking things that are designed for specific functionality and adapt them to space, as opposed to having to design something for space and then try and see how much functionality it can provide. If you can achieve that paradigm shift, the path towards commercialization becomes dramatically clearer.
Yeah, I mean, you're talking about where it's both applicable on Earth as well as on the moon, and therefore
No, what I'm talking about is that right now, if you want to build something for space, it is hyper optimized for size, weight, power, volume, and then you get to go off and say, if this is what I can do, what can I do with it? How much of the function that I need can be performed? If instead you can go and find somebody that's figured out how to make it work on a best practices basis on the Earth, and then go and optimize that for space, that's a fundamental paradigm shift.
Yeah, well, my opinion, this is sort of like the president of Microcosm, Jim Wirtz. His idea is, if you have very large structures, then you can have sort of Earth tech being used within this environment. And many of those very large structures are very large inflatables that you can construct on Earth, deliver 100-ton, with the 5 layers of inflatable habitats on the moon. A 100-ton payload could deliver a very large inflatable with 2-acre footprint. So Jim Wirtz's idea, is a very conceivable idea.
Jim, it was a former professor and colleague of mine. The truth be told, the answer, I think that's directly correct. However, I think there's also a need for what amounts to being hybrid structures. One of the things you see particularly in the latest burst tests with Sierra Space, they're going through and struggling and having to incorporate mechanical frames into into the inflatable structures. One of the things that we're proposing from the OASIS perspective is to combine inflatable systems with unfurlable frames, so that the inflatable becomes a pressure bladder, and the unfurlable frames react the mechanical loads. And we've looked at various designs for that, as well as how it is that you can do the interface between multi-layer fabric and ceramic and composite systems.
There, Alastair is on.
I'm right here.